Okay, well actually before, okay, no. No, never mind that. Ignore that. Okay. So, I did a mild sin in regards to my Advent of Code streams. I think I solved this off stream. I didn't submit it, so if I'm wrong, this will be a big egg on my face. But I think I solved this off stream. Oh, and also running it overnight didn't work. It was only like 75% done when I came back. So, issue here is that these things are way too fucking long to just calculate by going back and forth, doing the recursive thing. And that reminded me of a video, specifically about regex. Oh, actually, can I pull up the video? See if I can find it. GitLab. Okay, so the video it reminded me of is this video here about Cloudflare deploys really slow code.
To match this example,
and basically, I talked about regex parsers. Now, a lot of naive regex. Oh, what the? I was at just the perfect spot. What happened?
The next time on Tuesday, July 2nd.
Oh, that's because I'm hitting
HTML or Java, whether or not there's a non-capture. First, this first is the remaining 0 characters. Then the equal sign fails as the previous matches took.
So it talks about how a naive what's the word? A naive regex evaluator will go back and forth, and how that takes a long time. In fact, this takes big O of n squared, because essentially what you have to do is for each character, you have to scan all of the characters in front of it, or until there's a failure, and then backtrack. So that's big O of n squared. That's kind of a problem because we have a big fucking n. But the thing about regex is that regex define regular languages, which can always be turned into DFAs, which are always linear with the size of the input. So I thought, okay, well, what we have is kind of a similar situation. So in our example here, we have, like the first line is a question mark, question mark, question mark, dot, hash, hash, hash. Let's make a better hash. And what my naive implementation is doing is like, I go here, it's like, okay, well, let's try this as a hash. And then we move forward until it fails. And then when it fails, we go back and then try it as a dot. And then we just keep on doing and counting all of our successes. But that essentially means we're going back and forth a lot. And for the small things in part 1, not too much of a bad. When we get the larger things, that back and forth, not much of a problem. So I've tried to use the techniques of DFAs or regular languages to try to, okay, how can you just make this scan through the string only once? So, quick lesson on DFAs. Well, okay, let's just assume we don't have question marks, we only have dots and hashes. Well, how do we see if a string matches the condition that it is I believe it's 113 is the first one. So first we have a starting condition, which will change the color to a nice green for our starting condition. So this is where we start. And then go back to blue. And then, so from our starting point, any dot just goes back to where we started, because, doesn't really, like, we can have infinite number of dots, doesn't matter. And then for any hash we have, we go to our next state. Now, because we are only allowed to have one hash, immediately we have a dot going to our next state, and then any hashes we have don't go anywhere, because that would be considered invalid. And then again, we can have as many dots as we have, so we just have an arrow pointing to itself with another dot. We have another hash like this. And again, we're only allowed one hash, so this goes straight into a dot for another state, which could then point to itself however many times. And this is where we have the 3. So here we have a hash, and then unlike before, this goes to another hash to a state, and then another hash here. Now what's interesting is that, or not really interesting, but here, if we have a dot here, well, that's invalid because we needed a string of 3 hashes, so there's no output for a dot. And then we have a dot here, and then again we have infinite number of dots here, and then we mark the last two states as end states, or as possible end states. So now, let's just say we have hash dot hash dot hash hash hash. Well, we follow the path. So hash dot hash dot hash hash hash. Oh, look, and we ended in a valid state. Great. And then let's just say we have an extra dot at the end here, or let's just say we have an extra 3 dots. We don't in the actual thing, but let's just say we do. So hash dot hash dot hash 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 dot dot dot. Oh, we're back in an end state as well. So now, how do we deal with question marks? Well, with question marks, is that question marks could either be a hash or a dot. So, pretty much in each of these things, for each of these things, it could either be a dot or a question mark, a dot or a question mark, a dot or a hash, a dot or a hash. Pretty much in everything, we have an extra question mark. Now, you notice that means that from here, if we have a question mark, it can either go down or to itself. Well, yeah, that's kind of the problem, is that we don't know which it's taking. This is what is now known as a non-deterministic finite automata, NFA, which essentially means that any state, or in any state, a particular character can go to one of, for any particular character, you could have more than one possible places to go. So how do you make a non-deterministic finite automata act like a deterministic finite automata? You change your definition of state. So traditionally what you would do is, let's just say we label them A, B, oh god, did I make the circles too small? C, D, E, F, bucket G, H, and I. So so here we have our NFA, and just imagine that each branch also has a question mark in it. And then we have and then to turn this into a DFA, you start with your usual. You have your state A, and if you get a dot, that goes into state A. If you get a hash, this goes into state B. But if you get a question mark, well, this goes into a new state that we'll call AB. And then, as usual, A's, well, hold on. Since we already have an A, let's draw this a bit more correctly. You have a dot, goes back to itself as usual. If you have a hash, you go to B. But if you have a question mark, or you go to a new state, which we call AB. Basically, this state represents being either an A or B. So how do you work with this? Well, then in AB, if you get a dot, well, if you get a if you get a dot here, well, if you get a dot from A, you go back to A, but if you get a dot from B, you go to C. So a dot from AB goes to the state AC. And then if you get a hash, we'll get a hash from A goes to B. If we get a hash from B, well, it doesn't go anywhere, it fails. So a hash from B, from AB, just goes to the regular state B. And you essentially build this out. Now, and then the finished state is just whichever state contains one of the two finished states. Now, building this out requires essentially creating a power set of the original state set of states. Now, the size of a power set is 2 to the n, which, if we have anything larger than 32, is going to get way the fuck out of hand. But we can do this in a more lazy fashion. Basically, we start with this. From the 133, we built a regular state like this, and we do something similar to this, except instead of actually building out an NFA, what essentially we do is we just go character by character, and then have a map between all of the possible states we're in, and how many states, or how many paths are in that state. So we start. So again, we start. Let's just say in character 0. We start in state A. Then character 1, we read in a question mark. So that means well, that means we could stay in state A, in which case we'll have one element in state A. Or we can move to state B, in which case we'll have one element in state B. Then we get a second question mark. So again, the A here, I think it's A, B, and C. So the A here will get the 1 from A staying to itself. If B has a hash, or sorry, if A has a hash, it'll add 1 to B. If B has a hash, it'll fail, so that it goes nowhere. But if B has a dot, we move up 1 here. And then we get a third question mark. And basically, every time we get a question mark, we split off and then add things all together. And then if ever we get a dot, we just only go forward with the dots, and making sure that not only do we keep all the possible states we're in, but how many paths are in that state, because we just don't want, we don't just want the valid configurations, we want how many configurations there are. And as a result, instead of going back and forth through the state space a whole bunch of times, we can only go forward once. Now, of course, there is some extra overhead in regards to like keeping track of all these states, but the size of the dictionary here can never be more than the number of states, and we're only ever looping through that many. So it's basically big O over NM, where N is the size of the input string, and M is the number of states. That's stats. So, I hope I explained that well enough. Probably didn't, but, you know, I literally came up with this, like, minutes ago. So, showing off how it's implemented. Here we have our NFA and just a simple state, which essentially holds pointers to if we get a dot or if we get a hash, as well as a boolean for if it's a valid end state. And then there's some clever math, or not really math, but like programming that I don't particularly want to get into because it was kind of annoying to do. Well, not that annoying, but like from a list of the broken pipe patterns, so like 113, we construct the state. So for example, at state 0, a dot goes to itself, but a hash goes to the next one. Then then we count for each. Well, we loop the number of times the broken element pattern for that pattern, -1 obviously, because we got there from here. We then have the hash point to the next element, and then afterwards we have the dot point to the element after that, and then afterwards that dot points to itself. as well as the hash pointing to the next element, and we just keep on doing that, and then we get have the last two elements be set valid as true. Then for the actual count, it's again very similar to what I actually described verbally. Start, we have map type, which is essentially just a map from our state pointer to the size t, representing how many paths are in that state. So we initialize it with the current, where we start at state 0 with the size of 1. So then if we see a dot, then we create a new map, and then for each transition that leads to for each valid dot transition, we add that dot transition to our new map, and we just add the value. And then if it's a hash, do similar things. So if the current state can move in a hash direction, we add that hash direction to the new map. And then if it's a question mark, we essentially just do the same, but for both. So both hash and key. And then afterwards, we just we add up all of the values, but only the ones. So we add up the values, but only the ones where we end up in a valid state, and then we add all those counts together, and then return. So running on the sample input, here we get 525152, which is the right number here. Running on our actual input, we get this large ass number. And is that correct? I am so smart! I am so smart! I am a genius. I am a genius. Okay. Oh my god, I am so smart. Okay, so yeah, let's just clean up unused code and whatnot. In fact, we could use this. Do I want to... I almost want to keep... I almost want to keep my older cursive thing, because that was cute. Okay, I'll keep the function here, but I won't actually use it. I'll just yoink this, paste it here, and get rid of this unfold. Oh, and I need printfs. Have to be turned into my printfs, so that they can be disabled when running the entire year. And maybe don't print everything. Cool. Okay, I'm gonna take a short break and then I'm gonna start the stream for day 13.